Okay, thank you so much once again, Mr. Chairman. So I'm going to perform my second presentation, which somehow is related to the first presentation that I made previously regarding adhesive joints. But now we are going to test cohesive zone modeling technique, an adaptation to the impact loaded tubular adhesive joints. Impact loading is a load with high strain rate, and there are peculiarities that we need to adapt and adjust in the models so that we have accurate strength predictions. Uh, this work addresses that topic, and here we can see the main index of the presentation, which will include the objectives, the geometry and dimensions, materials, the characterization of the drop test, which will apply the impact to the specimens, a first validation of the numerical technique with the experimental data, and then the work will be mainly numerical. We will study different geometric modifications, such as the overlap length and adhesive thickness, and we will address also geometrical modifications at the level of the overlap, such as chamfers and fillets, so that we can maximize and propose an optimized geometry for this type of joints. We will conclude with the conclusions and suggestions for future work. The main objective of this work is to perform the numerical study of the tubular adhesive joints under impact, but to have confidence in our analysis, we will perform firstly a validation with experimental data, and then we will study the different geometric parameters, considering still tubular adhesive joints and three adhesives that range from strong and brittle to adhesives that are also strong but ductile, and adhesives that lie in the middle of these two. We will evaluate the p-delta curves, the maximum load, and the energy absorbed for the joints with the three adhesives up to failure. Here we can see the geometry of the joints. To the left, we have the validation joint. This is a typical single-up joint, which is many times used for validation purposes of models. And here we are going to validate with the experimental data of these joints. And then upon positive validation of the impact CZM, we are going to apply it to tubular overlap joints, in which we have two adherents, in which we have one inside of the other. So this is an overlap joint. Uh, and we have also the dimensions that we consider in the numerical simulations. We are going to directly apply properties that were already characterized as impact in a previous work, especially for the three adhesives. We had done an extensive study in a previous work in which we characterize the adhesives at different strain rates, and then we make an extrapolation to the testing rate that we are going to apply in our study. While the adherence, it was considered not dependent on the strain rate, and we considered properties that were also defined for this high strength steel, which has a yield stress of over 1 gigapascal, and in which we assure that in the simulations we do not enter plasticity in this adherence, so that we can focus on the plasticization and fracture process of the adhesives. This is details of the impact tests that we carried out, namely the drop test machine. We have one single up joint specimen attached to one end of the machine, while the other end of the specimen is going to be impacted with an energy of 40 joule, which is enough to promote the failure of the joints, and which will later emulate in the numerical analysis by applying an identical kinetic energy also with 40 joules, so that we can try to replicate the test specimen that we have in the experiments. The technique was formally validated. We can see in these graphics, firstly, the numerical reference and the experimental reference. These references are from a previous work in which we carried out the experiments and also the numerical data. the numerical results with reference properties. We are going to use properties that were characterized under static conditions, which we can see just for this example of the AV138, which are not the most suitable to model the dynamic impact behavior of the specimen. And here we have the numerical results which relate to the properties already specifically extrapolated to the impact load. So if we compare these results to the numerical reference and experimental reference, we can see that we have an average representation. Experimentally, we had always a little bit below the numerical data. The same occurs with the DP 8005 adhesive, also a very good representation of the numerical reference and shortly above the experimental value. And for the Chemtex, we are a little bit above the numerical reference and significantly above the experimental reference, but we consider that this has to do with some experimental effects and effects of the specimens during the experiments. So we are going to use these properties with our estimated properties, and we are going to carry out solely a numerical parametric study, either on basic geometric parameters of the joint and also some geometric modifications at the overlap, such as, for example, an adhesive fillet at the end of the adhesive, an inner chamfer in the tubular joint, and an outer chamfer in an attempt to mitigate the peak stress concentrations. We have also some details about the axisymmetric elements that we used in the numerical simulations. In the numerical simulations, we emulated the applied energy not by a drop test, but by a kinetic energy. We applied a pre-established velocity at a mass, an artificial mass, at one of the edges of the specimen, while the other edge was restrained. And with this, we aim to replicate the experimental conditions. The main parameters that we considered were the overlap length. We considered overlap lengths between 10 and 40 millimeters, always with an adhesive thickness of 0.2 millimeters. And we also varied the thickness of the adherents between 1 millimeter and 4 millimeters. These are the first results that we obtained numerically for the strength prediction. We can see that we have an increase in of the joint as expected as we increase the overlap length. In some cases, we are reaching a steady state value, but we can clearly see the effect of this variable, of this overlap length, depending on the adhesive, and which we summarize the results in this slide. Here we can see the results of the maximum load as a function of the overlap length. The Pmax always increases with the overlap length. The adhesives that have the highest increase, they are the AV138 and the XNR, while the DP adhesive shorts a little bit short of this behavior. The highest strength is for the AV138. And if we consider the dissipated energy at failure, which we can only see in this table, not in graphical form, we can see that the values are highest also for the AV and the XNR because they have the highest strength and also the highest displacement at failure. Here we can see the effect of the thickness of the adherents between 1 millimeter and 4 millimeters. This is 1 millimeter. And as we increase the thickness of the adherents, we can see that we have a slight tendency to have a higher maximum load, not as marked as the overlap length, but to have a shorter displacement to failure. And this happened for all of the adhesives. Here we have a summary of the results. We also have an increase in the maximum load with TP, with the thickness, but in this case, it is not as marked as the overlap. In terms of energy, on the other hand, we saw that the energy increases by reducing TP because although we have shorter displacements to failure, we have a higher increase in the maximum load. Different geometrical modifications were then tested. Here we can see the inner chamfer of the adhesive, the outer chamfer of the adhesive, and the adhesive fillet at the end of the overlap region. We considered all of these values. 90 degrees, it means that we don't have chamfer and we don't have fillet. So 90 degrees is the base condition. And then as we decrease this value, we start to have more pronounced modifications. These are the P delta curves for the inner chamfer. We can see that compared to the 90 degrees, which is no chamfer, there is actually no advantage in having this modification, and this is valid for all of the adhesives. And we can summarize the results here. Actually, from the no chamfer, we had a reduction of the strength, which is highest for the DP adhesive. If we consider, for example, the external chamfer, the results are basically the same. So this is the no chamfer condition, and with chamfer, there is not a strength improvement, but here we can see that there is a higher similarity between the different chamfers, and that is replicated in this graphic, in which we see that we have a lower strength, and also that we have in this case, also a decrease of the absorbed energy of the specimens. On the other hand, we saw that using an adhesive fillet actually has an effect of increasing the joint strength, because here we have the 90 degrees, and for some of the conditions, we actually have an increase in the strength of the joints. This is the results that we obtain, and actually we have improvements that go up to 35% for the AV, 19% for the DP, and 38% for the XNR. Here we can see a summary of all of the results. This is the base geometry. We have moderate improvements by changing the thickness of the adherents. The best results were obtained by the beta angle, which is the angle of the adhesive fillet, and by the internal and external chamfer, we have actually no advantage, and we have a loss of strength compared to the base condition. And these results are more or less qualitatively similar for all of the three adhesives that we tested. So these are the conclusions of the work that summarize what has been said. The technique was positively validated. We managed to emphasize on which modifications were beneficial for the strength of the joint and which ones were not. So with this work, we expect to have a contribution to the better design of this type of joints, and also have a tool that can help designers for the impact modeling of tubular joints. Thank you so much, Mr. Chairman. And this is my presentation. And if there is any question, please feel free to ask me.